Okay, this is Ed CNC Dude here. I'm gonna try to do an updated feed and speed thing here. I'm gonna incorporate CAD CAM Fusion and Mastercam in order to make the most of this. I mean, calculating feed and speeds should be a basic thing to learn. I find that all the fancy courses like Sandvik or ISCAR are very deep, almost like too deep. It's also my thought about teaching GD&T. It really should start off with simplistic terms, and for a machinist, pretty much how to read the blueprint, not necessarily how to do the inspection, but primarily what does it all mean, and then you can go to how do you measure it. Okay, you've probably seen this video with Mark Terryberry with his tractor, and actually you would use this in class, not a tractor, but I would say if you were driving down the highway, our highway is I-75, and you're right next to the Walmart truck going down the highway, you're both doing 70 miles an hour following the speed limit. Which wheel is rotating faster? And they'll say, oh, my car is rotating faster. I said, yes, so exactly. You're traveling the same mile per hour or feet per minute along the ground. So kind of like that basic, how do you teach the feet per minute thing? I think when we originally start class, we start doing some manual machining, and I'll say, how many RPM do you need to rotate that end mill? And I have a chart near the manual machining area I call it the chart for people that don't want to figure it out. You just look at it says 3/4 end mill, steel, like 800 RPM, whatever it is. I know that's wrong, but I'll bring over a little lesson because I'll have a thing on the board like how do you calculate RPM from surface feed and where do you get that data from? So I kind of like throw those tidbits out. And I'll actually, you could do a calculator. We have the formula. And then some of the milling machines have a calculator built into them. They don't have the SFM numbers. And the Haas machines actually have them also. So I'll use it as a learning thing every once in a while. Kind of like, what do you think the RPM of this should be? How do you know which one it is? So getting back to the surface feet per minute thing. So Mark's video, it just says inch version, and of course is a metric version. Very, very good. And I actually had this is my classroom here. And I had how to calculate speeds, and I did a playlist here. And I tried to capture any videos I could find, but it turns out some of them are my videos that I made, they're okay. They're not the best. I just added in the new Mark one to how to control your chips. This one here is very good. This actually had a Haas, how to run and set up a Haas mill series. And this one was also ISCAR. And the funny thing is, this is a good story. I drag race motorcycles, and I was up in Georgia at a national race, and I had watched this video series, and I used to see this guy. They called him ISCAR Rick. He worked for ISCAR. And there I am standing. I'm looking at him. It's like, hey, you're ISCAR Rick. And he goes, yeah. So he actually gave me a lot of data and stuff like that. He used to work for ISCAR. Now I think he works in Michigan for the HFO up there. So he actually gave me a lot of training stuff that he used. But this video here is pretty good.
This video was made possible through a grant from the Haas Corporation.
So let me shut the volume off. And they'll get a little bit on, of course, they're using inserted tools. And they'll talk a little bit about size, what kind of tool, revolutions. It's visual, so it's pretty good. You know, you could check how deep the step is. But some of the stuff is not as available as you think. Of course, Titan has the one pushing, and he was trying to see how much he could see if he could break an end mill. Of course, I don't think we wanted that. But it's a little example of kind of where we really should be going is if we utilize the good machining strategies that we can actually be more efficient. Not we're trying to like drag race. We'd want to be more efficient. So anyway, I capture some videos as I get them. And another one I found recently was from Helical Tools called In the Loop. And he's got a whole bunch of stuff here. And these are only the best ones I captured, but he's got a whole bunch of them. Fluke count, SFM, chip thinning, that's a big topic in the, I don't know, we all call it trochoidal milling, but it's the adaptive or dynamic style of milling. And what that all means, they actually have little diagrams here. This is excellent stuff. I think you can build your own course in your classroom utilizing these kind of tools. Like here, understanding helical interpolation. So he's actually talking about feeds and speeds and strategies, helix angles, high feed mills, ball nose, scallop heights, thread mills, chip breakers, what's a Walden flat. And I just captured a bunch of popular ones, but I know there's even more, and he'd come out with them every week. He's kind of a fun guy, so this is a good series, excellent series to go through. For myself, let me go back to my classroom. The first thing I had, and this is probably a shot I had from the 80s, it's a basic feed and speed shot. Oops, I thought I had the chart in here. There it is, right there. Feed and speed shot. Let me expand this. And, all right, there we are. Basic feed and speed shot with basic materials, not the color-coded and stuff like that. Pretty much you could tell aluminum, brass, iron, magnesium, steels, and a section on high helix mills for the stainlesses. And there's some other data down here for coatings, like you can bump it up for coatings or light or deep axial. Axial would be deeper and radial would be sideways. I think of radial tire and an axle. And his basic surface feed per minute and the chip load. Now, the chip load on all these old shots are based on 50% step over, like 50% of the end mill. So if you are using adaptive, 3D adaptive, like in a Titan class or something like that, or Mastercam dynamic milling, if you're only engaging like 20%, your chip is thinner, back to the chip thinning thing. And there is a way to calculate it. I think there's a FS Wizard app you can calculate. There's some other ones. I think Helical actually has a very good catalog. Let me see if I can find that. Here it is. Here, this is just a screenshot. It says Machining Advisor Pro. Give you the material, type of tool path you're going to use, how deep you're going to go, how much step over, and you can play with all these functions here, and it's pretty cool. I don't know if the Philip Machinists app has the deeper topic on the feeds and speeds. That would probably be a good add-on. So this thing is pretty good, the helical one. Having a couple of basic shots is way better than I think what we're getting in for training nowadays. So I got in the loop, I have a couple of mine, I got a couple of basic shots, and I did find, let me see here, Haas tooling. I noticed when I was in the Haas tooling site, when I was starting to use the tools when we were in Project MFG, and they had some data in there. And of course, these are more professional. These have color code because they're P, M, K, N, super alloys, all that kind of stuff. But kind of the same idea. This is low. Of course, it says low alloy still. It doesn't really say what it is. Of course, that's would be a low carbon. But if you're in, let's say, steels, low alloy, and you got HB would be Brunel hardness, and HRC would be Rockwell hardness. So a lot of feed and speed charts will reference hardness. If you're not specific, or sometimes I found if I couldn't find the metal, I would find a similar metal hardness. I would use that for feed and speed data. And then I got right here, cutting speed, SFM. So it's probably a good classroom thing to do like once a week and just have them calculate, do the calculation, give them the data, like what I need the RPM for a half-inch end mill using 1018 steel with a surface speed of, let's pick one here, 275. Tell me what the RPM would be. And do a bonus now, give me a feed rate. Can then do the feed rate calculation because you need RPM in order to use this 8/10 to 1,006/10. So for me, I always go in the middle because then you got a little bit, I can go faster, I can go slower, even at the machine. And then later on, you can get into the chip thinning topic and the high speed machining or high energy HEM, HSM, whatever you want to call it. So I would arm yourself with a couple of charts. I give everybody a couple of charts and handouts, and then have them do this, do feed and speeds. Now, when we get into the CAM area, let me pull up just any old job here. Let me switch my team. Give it a second. All right. We're all familiar with the Titan stuff. Let me pull up a Titan project. Here it is. We'll go with the old Titan 1M. And I have demo. This one's probably good. It's got 63 versions, so I've probably been opening that a lot. All right. So in my class, let me go backtrack here. I'm in my Google Classroom. Let me pull that up. And when I'm in my class here, I have whether I'm teaching Mastercam or Autodesk, I can kind of go, if we're doing a Titan series, I would do Titan 1, 2M, and then I'll talk about doing logos have them do a logo or engrave your own name on it. And we'll keep on going on, then we'll get into 3M, and then we'll talk about soft draws, because the round soft draw is probably the easiest one to make. And we'll continue on, then we'll do a blueprint talk, like how to create a blueprint in your CAD system. And then we'll go along, and then we actually revisit the Titan 1M in steel, and then it's time to learn feeds and speeds. So now we do the feed and speed lessons, because we'll make the part this time out of steel, out of cold rolled steel, because we had a whole bunch of it. It's pretty cheap, and how much a big learning bump that is. So let's get out of that. And then here, okay. So if I am in the CAM side here, there we go, 1M, and I go to, let's go to the second end mill, edit. Okay, because right in here you got surface speed. What does that mean? What's this mean? We got RPM, and in here I have some presets that say adaptive pocket contour. So I made the tool library, and all the students get it, and I have it set up to be all aluminum, and the machine that's got the lowest max RPM, which would be the TM machine. So nothing's faster than 6,000, number one. And they pick in here what are they doing, adaptive, pocket, or contour. And then this would pretty much self-populate. And in this case, it also gives the feed rate, 4 thou per tooth. And these have like nice, good demonstrations. There's your 50% step over, by the way. And then you get some other settings like optimal load settings, stuff like that. So you can do that, and when you revisit steel, then say, now I want you to redo this project, but now look at your chart, and then tell me what all this is going to be. Actually, make a copy of this program and reprogram it for steel. And we'll review it, and then I'll give them some parameters, like we're using 3 fluted end mills in the aluminum. We're going to use 4 fluted end mills, or 4 or 5, with the steel. We are going to use cutting taps, not forming taps, and that requires us to change the drill out. So I'll have to also do like which drill are we going to use. And that's about it. So we just change whatever end mills get swapped to 4 or 5 fluters, and cutting taps and cutting tap standard drills. And then we'll do the steel, and then we talk about maybe taking less of a step over, or how deep do we need to go. I think it's a really good, simple way to teach other materials, and it kind of makes more sense because they're a couple, 3 to 5 months into the program, and you can kind of think of like, oh, what does feed and speed really mean? Because in the beginning, we just make parts. So now we're getting into thinking about it. What do we need to change? Which way are we going to do it? And how easily that went. So what did I cover? The feed and speed charts with the Haas. So that I would go and dig in the Haas stuff. So if I was in I'm in the end mill section right here. Let me go into, they even have it over here, inch. Let's see, size. This size? Diameter, yep. Let's go just right to ½ inch, right? Starts narrowing down. And they have these categories, HEM, HEPM. I'm not quite sure what they all mean. But they also have categories here for what are you cutting. So we're going to say, oh, we're cutting aluminum, right? Which, what is that now? Carbide, we're doing a carbide. And let's go uncoated. And we'll be, let's see, square end. Wow, that thing keeps on moving all the time. Length of cut, number of flutes, they're all 3 fluters. And there we go, we're down to 2. All right, let's click on this one. And I don't know if that's the teacher discount, but we all get discounts. And right here it says technical documents, speeds and feeds, side cutting HSM. And this one actually has SFM, kind of a lot of data stuff. And actually right below it, it's giving you RPM. Of course, some of these RPMs are unachievable, like, let's see, 61,100 RPMs. So, because that's 8,000 feet per minute. And there's some other ones here. Cast out, slotting, the long, crazy formulas. I like using the simple formula, the 3.82, blah, 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 by SFM, by whatever, diameter. Anyway, so that's kind of my, I think, build your own feed and speed course personally. And you just keep on getting a little deeper and a little deeper. And I like it to learn it myself because we started to get into other metals. Somebody wanted something made out of titanium, so we had to go look that up. They supplied the metal. We had to make a prototype golf club, so we actually cut a few out of aluminum just to make sure it worked. And then when we got the material, we had our feeds and speeds, our tooling right, and everything came out great. So that's my opinion on teaching speeds and feeds. Okay, this is Ed Doherty, the CNC dude, signing off.